Good morning, girls. Girls, we have two, three more questions from the exercise chapter, that is magnetism, magnetic effect of electric current. And today we are going to finish these three questions starting from the 13th one. Question says that a coil of insulated copper wire is connected to a galvanometer. A coil of insulated copper wire is connected to what? It is connected to a galvanometer. You know, galvanometer is an instrument which tells you the presence of the current. Now, what will happen? There are three conditions given. What will happen if the bar magnet is pushed into the coil? It is withdrawn from inside the coil and held stationary inside the coil. Okay. Now, the three conditions are, see, 13. This is a coil connected to the galvanometer. In the first condition, they are saying that what will happen when the bar magnet is pushed uh, into the coil. Bar magnet is pushed into the coil. Right. Now there's a bar magnet. If we are pushing it inside the coil, what do you think what will happen? The current will be induced in the coil and the galvanometer will show the deflection. Okay. So your first answer is there will be deflection in the galvanometer. Okay, and it will be just a momentary deflection. Okay, when it is pushed into this is pushed into the coil. And why there will be a deflection? Because the current is induced in the coil. You have studied this before, children. So there will be a momentary deflection in the galvanometer as the current is induced in the coil. Now, second point. The second point is what will happen if it is withdrawn from inside the coil. Means we are taking the bar magnet and pushed, not pushed exactly, withdrawn from inside. Yeah. Now, when the bar magnet is withdrawn from inside, first we have taken it inside the coil. Now, if you are taking it out, there will be a deflection in the galvanometer, but the direction of the current will change and the direction of the deflection will also change. Okay, so what will we write? There will be deflection in the galvanometer, but in the opposite direction. You know that the current is induced in the coil. Once it is inside, the bar magnet is inside, the current is induced, the direction of the current will be different and there will be a deflection in the galvanometer. When we take this bar magnet out, there will be current induced, the direction of the current will change, and therefore the direction of the deflection in the galvanometer will also change. So this is the second point. There will be deflection in the galvanometer, but it will be in the opposite direction. Okay, because what we are doing now, we are taking the bar magnet outside or we are withdrawing it. Then third point is if we just held stationary, obviously when the current when there is no current, there is no deflection. So when the bar magnet is held stationary in the coil, there will be no deflection in the galvanometer, right? Galvanometer. You know electromagnetic induction phenomenon. What happens when this coil, we are just um, bringing this bar magnet inside and outside means there is a relative motion inside. Then when there is a relative motion in the magnet or in the coil, then only the current is induced. But as you are keeping it stationary, you are just keeping it stationary, so therefore there will be no deflection in the galvanometer, and no deflection means no current is flowing in the coil. Okay, or we can say no current is induced in the coil because the bar magnet is not in motion, it is just held stationary. Okay, this is question number 13. These are the three conditions. You can write the answer in your own words. 14th, two circular coils A and B are placed close to each other. Okay, if the current in the coil A is changed, will some current be induced in the coil B? Give reason. What do you think? What will happen? Two circular coils. Obviously, what will happen if there are two circular coils A and B which are placed close to each other? Current is flowing in the coil A. Okay, now when the current is flowing in the coil A, that will start behaving like a magnet. Okay, when coil A will start behaving like a magnet, the magnetic field around, if the current is changed, now when we are changing the current, the magnetic field around A will change, and definitely that will bring some change in the coil B. Okay, and we are going to write the reason now. 13th one. We write yes. Will some current be induced in the coil? Yes, we write yes. There will be current. There will be current induced in coil B. Now it is firstly, see, this is coil A, this is coil B. A and B, obviously they are connected to each other, right? When the current which is flowing in A, it is changed. When the current flowing in A is changed, definitely the magnetic field around A will change, and that will affect what? The magnetic flux. You know what is magnetic flux? I had explained you. Magnetic flux. Okay, I'll write the answer, you will understand that when the current in coil A changes, the magnetic flux the magnetic flux for coil B will change. That gives rise to induced current in coil B. Okay, so the answer is yes, there will be current induced in coil B, because when the current is allowed to flow in coil A, okay, magnetic field will be generated because this will start behaving like a magnet. Now, when the current is changed, they are asking you, see the question again. See the question again. They are saying that if the current in the coil A is changed, will some current be induced in the coil B? So you will write yes, because when the current in the coil A is changed, the magnetic field associated with A will change, and therefore the magnetic flux which is connected to or which is linked with coil B, that will also change, and therefore the current will be induced in coil B. And yes, this is the answer. Okay, so therefore I've written, you can check out once again, that there will be current induced in coil B. Yes, this is the answer actually. How? When the current in coil A changes, this will affect the magnetic field. Now because of the change in the magnetic field, the magnetic flux for coil B will change, right? And that will give rise to the induced current in coil B. Okay, so here you can add one point here, that when the current in coil A changes, the magnetic, I'll put a star and write, the magnetic field, okay, changes. Hence, the magnetic flux for coil B will also change, and that will give rise to the induced current in coil B. Okay, now question number now which one? 15th one. Children, I hope you remember what is magnetic flux. You will go through the explanations of my previous videos and you will try to understand what is magnetic flux. Okay, so this is one work for you. You will find out what is magnetic flux. I have used this word when I was explaining you magnetic field. Okay, so you can go through those videos and check out what is magnetic flux. Right, now in the 15th one they are saying state the rule. Now there are we have studied in this chapter some rules. State the rule to determine the direction of the magnetic field. Number 1, magnetic field around a straight current carrying conductor carrying current. Okay, number 1, magnetic field, we have to find the direction of the magnetic field. Okay, now direction of the magnetic field, where direction of the magnetic field produced in a straight conductor, straight current carrying conductor. Now, do you remember which rule we have to apply? The answer for this is right hand thumb rule. Okay, right hand thumb rule. Right hand thumb rule, you know what we've done? This right hand, this is my right hand, this is thumb. This curled finger shows the direction of the magnetic field. And what does this show? This thumb shows the direction of the current. So this is a right hand thumb rule which we use for the direction of the magnetic field, straight for the straight conductor, and that is current is flowing through that conductor. Okay, this is, and you also will write, you will explain the rule. Okay, so I am not writing the whole thing again here. You will find out the direction of the magnetic field in a straight current carrying conductor by which rule? Right hand thumb rule, and you will explain that rule and write in detail. Number 2, force experienced by a current carrying straight conductor placed in a magnetic field which is perpendicular to it. Force experienced by a current carrying conductor placed in a magnetic field. Force, direction of what? Direction of the force. Direction of the force which is experienced by the current carrying conductor. Okay, current carrying conductor which is placed where? It is placed in a magnetic field. So when we were studying electric motor, before that we have studied this. Now which is the rule which is being applied here? Fleming's right hand or left hand? Left hand rule. Okay, Fleming's left hand rule is used. If you remember, how do we use the Fleming left hand rule? What? The 3 fingers, right, mutually perpendicular to each other, and first finger shows the direction of the magnetic field. What does this show? Thumb. And what does center finger show? The center finger shows the direction of the current, and the thumb shows the direction of what? It shows the direction of the force which is acting on the, which is experienced by the current carrying conductor. Okay, this is Fleming's left hand rule, and this also you will write in explain this rule. Okay, so I hope you know what is a Fleming's left hand rule. When the 3 fingers are perpendicular to each other, first finger will show the direction of the magnetic field, the center finger will show the direction of the current, and the thumb will show the direction of the force which is acting on the current carrying conductor which is placed in a magnetic field. Now, number 3. Number 3 is the current which is induced in the coil due to the rotation of the magnetic field. This is also we have studied. So third point. Third point. What is the third point? I write it down in short. Current induced. The current which is induced in a coil due to the motion of the magnetic field or due to the rotation of the magnetic field. We have studied just before generator, and the answer to this is what? Fleming's right hand rule. Okay, how do we apply the right hand rule, children? Great. When we stretch, see, when we stretch the 3 fingers of the right hand such that they are mutually perpendicular to each other, what will happen? The first finger will show the direction of the field, the center finger shows the direction of the current, and what does this show? What does the thumb show? The thumb shows the direction of the motion of the conductor. Okay, so again, the first finger, that is a forefinger, will show you the direction of the field. I told you how to remember first finger with field. Thumb will show the direction of the motion of the conductor, and the center finger will show the direction of the current. Always remember, the center finger will give current, the first finger will give the direction of the what? Magnetic field, and the thumb will give you the direction of the motion of the conductor. So again, you will explain the rule and write in your own words. So children, this completes your exercise questions from the chapter Magnetic Effect of Electric Current. Okay, 13, 14, 15. Now in between the chapter, if you have any doubts, you can ask me, and you study well for your test also. You have test in the next week most probably. Okay, thank you, have a nice day.